I'm Grishma and you are watching my channel G Tutorial. This is my second video on calculus of complex functions. In my first video, I have described what is a complex variable and we have done some problems from complex variables. If you have not watched the video, I will be giving the link below my video. Here we are going to discuss about complex functions and some related topics of this complex functions, and we will be doing more problems. If you are watching my video for the first time, please subscribe my channel for more AI ATC related videos. Now let us get to our questions. First we can see what is a complex function. If for each value of the complex variable is z, which is equal to x plus iy, in a given region R, we have one or more than values of w, which is equal to u plus iv, then w is said to be a complex function of z, and we can write w as u of xy plus I v of xy, where u and v are real functions of x and y. That is, w is a function. It's a complex function of the complex variable z, which is obtained by giving various values for z in a region, from a region R. That is, for giving different values for x and y, we obtain different complex variables z. And for that complex variables, we will be obtaining a function w in the region R. And this function w can be expressed as u of xy plus iv of xy, where this imaginary part and real part, each of them are functions of x and y respectively. Now for each value of z, if there corresponds only one and only one value of w, then w is said to be a single valued function. Otherwise, it is a multi-valued function. By observing the examples, we will be understanding more about the single value function and multi-value function. If w is a function of z, that is, if w is equal to 1 by z, then it is a single valued function which is defined at all planes, all points of the z plane except at z is equal to 0. That is, if 1 by z means 1 by x plus I y. For each value of x and y, there is only one value for w. So, w is a single valued function. Now next function is w is equal to root z. This is a multi-valued function except at point z is equal to 0. That is, if we are substituting, z is x plus iy. If we are substituting 1 for x and y, we will get w as root of 1 plus 1y. And similarly, if we are substituting minus 1 and minus 1 for x and y, then also we will obtain same w as the answer as a function. So this is a multi-valued function. Both points result to same function. Okay, now we can move on to the next portion. We are all familiar with exponential functions e raised to x. E raised to x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus etc. Similarly, exponential function for a complex variable, it is denoted by e raised to z. We know that z is equal to x plus iy. So e raised to z can be expressed as 1 plus z by z factorial plus z square by 2 factorial plus z cube by 3 factorial plus z raised to 4 by 4 factorial plus etc. up to infinity. Okay, we know that z is equal to x plus iy. We are putting x is equal to 0. So z is equal to 0 plus iy, or z is equal to iy. And we are substituting in this equation. So e raised to z is equal to 1 plus, instead of z only iy exists. So iy by 1 factorial plus iy the whole square plus 2 factorial plus iy the whole cube plus 3 factorial plus iy the whole raised to 4 by 4 factorial plus etc. Which is equal to 1 plus iy by 1 factorial, which is 1, plus iy the whole square is I square is minus 1. So minus y square by 2 factorial plus I square is minus 1 and I square into I is I cube minus I y cube by 3 factorial. I square the whole square is I raised to 4. So that is minus 1 the whole square, that is plus 1. So plus 1 y raised to 4 by 4 factorial plus I raised to 5 is I y raised to 5 by 5 factorial plus etc. Now we can group the real terms and imaginary terms. 1 plus, so 1 minus y square by 2 factorial plus y raised to 4 by 4 factorial plus I into imaginary terms of y by 1 factorial is 1. So y minus y cube by 3 factorial plus y raised to 5 by 5 factorial minus etc. We know that this is the expansion for cos y. So we can write this is cos y plus I and this is the expansion of sin y. So we can express e raised to z as cos y plus I sin y when x is equal to 0. We know that e raised to z is equal to e raised to x plus iy. Or we can write e raised to x into e raised to iy. E raised to x into, we had obtained e raised to iy. E raised to z is e raised to iy is equal to cos y plus. We can substitute for e raised to iy as cos y plus I sin y. Cos y plus I sin y. Okay. We know that the complex variable can be expressed in polar form as r e raised to I theta. Sorry, r into cos theta plus I sin theta. From here, we have seen that e raised to iy is cos y plus I sin y. So cos theta plus I sin theta can be expressed as r e raised to cos y plus I sin y is e raised to I y. So e raised to I theta. So z is equal to r e raised to theta. This is the polar form of exponential function. Okay. Next is analytic function. This is one of the important topics from complex functions. A function which is single value and possesses a unique derivative with respect to z at all points of the region R is called an analytic or regular or holomorphic function of z in that region R. A function which is single valued and also possesses a unique derivative. Such a function is called analytic function. And a point at which an analytic function ceases to possess derivative is called a singular point. The necessary and sufficient condition for a function to be analytic are the function w is equal to f of z, which is u of xy plus I b of xy to be analytic in the region R, dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y, which are the partial derivatives of u and v with respect to x and y, are continuous functions of x and y in the region R. The next condition is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. These equations are known as Cauchy Riemann Equation or briefly CR equations. In polar coordinates, we can express x is equal to r cos theta, y is equal to r sin theta, and the complex variable z is equal to x plus iy is equal to r e raised to I theta. W is a function of z. It is function of r e raised to I theta. Actually, w is equal to u plus ib, which is equal to f of r e raised to I theta. You can represent this as equation 1. So we are trying to obtain the CR equation in terms of polar coordinates. Differentiating this equation 1 partially with respect to r. So dou u by dou r plus I dou v by dou r is equal to f of f dash of into, we are differentiating with respect to, partially with respect to r. So e raised to I theta is a constant into e raised to I theta. First derivative of r is 1. So this is equation 2. So we are differentiating equation 1 partially with respect to theta. So we will get dou u by dou theta is plus I dou v by dou theta is equal to derivative of function f of z. Now we are differentiating with respect to theta. So r is a constant. E raised to I theta, derivative of e raised to I theta is I is a constant. So I e raised to I theta. So comparing equation 3 and equation 2, we can replace f dash of r e raised to I theta into e raised to I theta by dou u by dou r plus I dou v by dou r. So dou u by dou theta plus I dou v by dou theta is equal to, instead of this, e raised to I theta r I into dou u by dou r plus I dou v by dou r. That is dou u by dou theta plus I dou v by dou theta minus, we are separating real terms and imaginary terms, multiplying ri to both the terms, we put in I into I square, that is minus 1. R dou v by dou r plus I r dou u by dou r. Now equating real terms and imaginary terms. Dou u by dou theta is equal to minus r dou v by dou r, and dou v by dou theta is equal to r dou u by dou r. So I am dou u by dou theta is equal to minus r dou v by dou r, and dou u by dou v by dou theta is equal to r dou u by dou r. I want dou u by dou r. So I am expressing dou u by dou r is equal to 1 by r dou v by dou theta. 1 by r dou v by dou theta. And dou v by dou r. Dou v by dou r is equal to minus 1 by r dou u by dou theta. This is the CR equation in terms of polar coordinates. You just need to by heart this. Dou u by dou r is equal to 1 by r dou v by dou theta, and dou v by dou r is equal to minus 1 by r dou u by dou theta. This is the CR equation in terms of polar coordinates. Next topic is harmonic function. Any solution of Laplace equation dou square phi by dou x square plus dou square phi by dou y square is equal to 0 is called a harmonic function. Let the function f of z is equal to u plus iv be an analytic function. That is, it satisfies Cauchy Riemann equation. That is, dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. So we are differentiating equation 1 partially with respect to x and equation 2 partially with respect to y. We will get dou square u by dou x square is equal to dou square v by dou x dou y, and this is equation 3, and equation 2 is differentiating partially with respect to y. Dou square u by dou square y is equal to minus dou square v by dou y dou x. Let us assume that dou square v by dou x dou y is equal to dou square v by dou y dou x. Then adding equation 3 and 4, we will get dou square u by dou x square plus dou square u by dou y square is equal to, both of them are same. So on adding we get 0. So we can see the function u of xy satisfies Laplace equation. Similarly, if we are differentiating the first equation with respect to y and second equation with respect to x, we will obtain dou square v by dou x square plus dou square v by dou y square is also equal to 0. So we can see that u and v are harmonic functions. That is, it satisfies Laplace equation. That is, dou square phi by dou x square plus dou square phi by dou y square is equal to 0. Now let us do some problems from these portions. First, let us do a problem from harmonic functions. For what value of lambda, the function u of xy is equal to lambda x square plus y square minus 2xy was a harmonic function. Given the function u of xy is harmonic, that is, it satisfies Laplace equation. That is, dou square u by dou x square plus dou square u by dou y square is equal to 0. So first we have to find dou u by dou x. U is equal to, u of xy is equal to lambda x square plus y square minus 2xy. So dou u by dou x, differentiating this partially with respect to x. Lambda x is 2, lambda x square is 2 lambda x plus y square is constant, so its derivative is 0 when we are differentiating partially with respect to x. Here minus 2xy is minus 2y. Dou square u by dou x square. Again partially differentiating with respect to x. 2 lambda minus 2y is 0. Dou u by dou y, partially differentiating with respect to y, equal to 2y minus 2x. Dou square u by dou y square is equal to, again partially differentiating with respect to y, 2. So dou square u by dou x square plus dou square u by dou y square is equal to 2 lambda plus 2, which is equal to 0 since it satisfies Laplace equation. 2 into lambda plus 1 is equal to 0, or lambda plus 1 is equal to 0, or lambda is equal to minus 1, which is the correct answer. Next, this is the next question. For what value of a, the function u of xy is equal to e raised to ax cos y as a harmonic function. Again, this is a harmonic function, so u satisfies Laplace equation, that is dou square u by dou x square plus dou square u by dou y square is equal to 0. So we have to find partial derivatives with respect to x and y of u. U is e raised to ax cos phi y. So dou u by dou x is differentiating partially with respect to x. E raised to ax is a e raised to ax. Cos phi y is a constant here. Dou u by dou y is differentiating with respect to y. So here e raised to ax is a constant. Differentiation of cos phi y is minus 5 sin phi y. Minus equal to minus 5 sin phi y. Dou square u by dou x square is a square e raised to ax cos phi y, and dou square u by dou y square is equal to 5 into 5 25 e raised to ax sin phi, sin is the differentiation of sin is cos phi y. So as it satisfies Laplace equation, dou square x plus dou square u by dou x square plus dou square u by dou y square is equal to a square e raised to ax cos phi y plus minus 25 e raised to ax cos phi y is equal to 0, or a square e raised to ax cos phi y is equal to 25 e raised to ax cos phi y. E raised to ax cos phi y get cancelled, so a square is equal to 25, or a is equal to root of 25, that is 5. This is the required answer. Now we can do some problems from analytic functions. This is the first question. For what values of lambda, the function f of z is equal to x square plus lambda y square plus 2xyi is analytic. If the function f of z is analytic, then it satisfies Cauchy Riemann equation. This is of the form u plus ib, where u is the real part, that is x square plus lambda y square, and b is the imaginary part, 2xy. it satisfies Cauchy Riemann equation, that is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x, since it is an analytic function. So we have to find dou u by dou x. Dou u by dou x is 2x. Dou u by dou y is 2 lambda y. And dou v by dou x is 2y, and dou v by dou y is 2x. So we have to find lambda. So dou u by dou y is where lambda is, that is 2 lambda y. So we have to take this equation. Dou u by dou y is equal to minus dou v by dou x, that is 2 lambda y is equal to minus dou v by dou x, that is minus 2y. 2 and y gets cancelled, so lambda is equal to minus. Next question. This is the next question. For what value of r, the function f of z is equal to x plus py plus I q of x qx plus I ry is analytic. The function is analytic, it satisfies CR equation. F of z is equal to x plus py plus I qx plus ry. Here u is x plus py and the imaginary part is v, qx plus ry. Cauchy Riemann equation is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. So dou u by dou x is equal to 1, and dou u by dou y is equal to p, dou v by dou x is equal to q, dou v by dou y is equal to r. We have to find r, the value of r. So dou v by dou y, it appears in this equation. So dou u by dou x is equal to dou v by dou y. Dou u by dou x is 1, and dou v by dou y is r. So r is equal to 1. Next question. This is the next question. Find p such that the function f of z expressed in polar coordinates as f of z is equal to r square cos 2 theta plus I r square sin p theta is analytic. Here function is expressed in polar form u plus iv. It is r square cos 2 theta plus I r square sin p theta. U is equal to r square cos 2 theta and v is equal to r square sin p theta. In polar form, the Cauchy Riemann equation is given by dou u by dou r is equal to 1 by r, dou v by dou theta, and dou v by dou r is equal to minus 1 by r, dou u by dou theta. So we have to find we have to differentiate u and v partially with respect to r and theta. Dou u by dou r is equal to 2r, cos 2 theta is a constant. Dou u by dou theta, then r square is a constant. Differentiation of cos 2 theta plus 2 theta is minus 2 sin 2 theta. So minus 2 r square sin 2 theta. Dou v by dou r is 2r sin p theta, and dou v by dou theta is p r square cos p theta. We have to find p. Now dou u by dou r is 1 by r, dou v by dou theta. So dou u by dou r is 2r cos 2 theta is equal to 1 by r, dou v by dou theta is p r square cos p theta, or 2r cos 2 theta is equal to p. R square and r get cancelled, so r cos p theta. R and r get cancelled, so 2 cos 2 theta is equal to p cos p theta. Similarly, dou v by dou r is equal to 1 by r minus 1 by r, dou u by dou theta, or dou v by dou r is 2r sin p theta is equal to minus 1 by r minus 2 r square sin 2 theta. Minus and minus r and r square to cancel. 2 and 2 gets cancelled. So sin p theta is equal to sin 2 theta, or p is equal to 2. From here also we have taken p is equal to 2. So p is equal to 2 is the required answer. Next is Milne-Thomson's method. This is actually a method to determine the analytic function when u or v is given. We know that z is equal to x plus I y. The conjugate of z, that is z bar, is x minus I y. From here we can express x and y as x is equal to z plus z bar by 2 and y is equal to z minus z bar by 2i. Then the function f of z is equal to f of xy, f of u plus I, or you can express, this is equal to u plus iv, or u of xy plus iv of xy. We can replace x and y by z plus z bar by 2 and z minus z bar by 2i. So you can write u of z plus z bar by 2, z minus z bar by 2i plus I into v of z plus z bar by 2, z minus z bar by 2i. Now we can consider this as an identity in two variables z and z bar, and put substituting z bar is equal to z. We will get the function f of z as u of z bar is equal to z. So z plus z by 2 is 2z by 2, which is equal to z. U of z, z minus z bar is z, so z minus z by 2 is 0, plus I into v of, this is equal to z and this is equal to 0. So this is same as substituting the equation 1. There is x is equal to z and y is equal to 0. We have seen the same result is obtained if you are substituting x equal to z and y is equal to 0. So we can see the steps involved in solving a problem if u and given and we are asked to find the analytic function. 3 steps are involved. We can see those steps. Now we can see the 3 steps involved in doing this kind of problem. First step is, we know that function f of z is u plus iv. First we have to find the derivative of the function f of z, that is with respect to x, that is dou u by dou x plus I dou v by dou x. We know that the function is analytic, so it satisfies CR equation, that is dou u by dou y is equal to minus dou v by dou x. So we can express dou u by dou x plus I dou v by dou x as minus dou u by dou y, minus dou u by minus I dou u by dou y. We are replacing dou v by dou x by minus dou u by dou y. Next step is replace x by z and y by 0. And the third step is, we have obtained a function only in terms of z. We have to integrate f dash of z. We will get f of z, and from there we can find either u or v. The real part of the f of z gives u and the imaginary part gives v. So if one among them is given, we can find the other one. U and v. U is called the complex conjugate of v and v is called the complex conjugate of u. Complex conjugates. U and v are called complex conjugates of each other. Now we can do some of the problem from this. This is the first problem. The complex conjugate of the function u of xy is equal to 3y square minus x cube. We are asked to find the complex conjugate of u. U is given, that is we have to find v. We have studied by Milne-Thomson's method. The 3 steps are involved to find the complex conjugate, or actually the analytic function. First step is f of z is u plus iv. We have to find f dash of z, that is here u is given, so dou u by dou x plus I dou v by dou y dou x. As it satisfies as it is an analytic function, it satisfies CR equation. So dou v by dou x can be expressed in terms of dou u by dou y. That is dou u by dou x is equal to minus I dou u by dou y. Since dou u by dou y is equal to minus dou v by dou x. Now we have to find dou u by dou x and dou u by dou y and substitute in this equation. U is 3xy square minus x cube. So dou u by dou x is differentiating this with respect to x. That is 3y square minus 3x square. And dou u by dou y is 3 2 6 xy. Substituting in this, we will get f dash of z is equal to dou u by dou x is 3y square minus 3x square minus I 6xy. The second step is replace x by z and y by 0. So we get f dash of z is equal to y is 0. So this term 0 minus 3z square minus this term is also 0 since y is 0. So this is the f dash of z. Next step is integrate. So we will get integration of f dash of z is f of z is equal to integral minus 3 z square, which is equal to minus 3 z cube by 3 or equal to minus z cube. So f of z is minus z cube. That is f of z is equal to z is x plus I by the whole cube. What is equal to minus a plus b the whole cube is a cube plus b cube plus 3ab into a plus b equal to minus x cube minus I y cube plus I into 3x square y minus 3x y square. Opening the bracket, we will get minus x cube plus I y cube minus I 3x square y plus 3x y square. Then the real terms are minus x cube and plus 3x y square plus I into y cube minus 3x square y. So we are asked to find the complex conjugate of u, that is we have to find v. We are given u as 3x square minus x cube and we are asked to find y. The imaginary part of this function f of z is the complex conjugate of u, that is v. V is equal to imaginary part, that is y cube minus 3x square y. This is the required answer. Y cube minus 3x square. This is actual method of doing this problem. There is a shortcut for this problem which gives us the result in just 2 or 3 minutes. We can refer to that too. The shortcut for this problem is we are given 4 options. We are asked to find the complex conjugate of u. We know that since the function is analytic, it satisfies CR equation. So dou u by dou x will be equal to dou v by dou y. Here we are given u. We can find dou u by dou x. Dou u by dou x is differentiating this with respect to x, which is 3y square minus 3x square. Similarly, from this option, we are asked to find the complex conjugate, that is V. We can find dou. So these are V. We have to find which V suits our function. So dou V by dou Y from each of us. This we need to find is dou V by dou Y, which will be equal to this dou U by dou X. So differentiating each of this with respect to Y. 3y square minus 6x, which is not the required answer. Next is 3y square minus 6xy. This is also 6xy. Next option is y cube plus 3x square. This is 3y square plus 3x square, which is also not the answer. Next one is 3y square minus 3x square. Check. This is the required answer. So we can say that this is the correct answer. Just we have to do is we have to satisfy the CR equation. So dou u by dou x, we have to find dou u by dou x. We have to find dou v by dou y from these options. Which among this matches the dou u by dou x is the required answer. Only this much is enough to do such kinds of problem. Thank you. This is the next question. Find the complex conjugate of the function u is equal to xy. We have to find u is given, we have to find v. What we have to do is, we have to satisfy the CR equation. Dou u by dou x is equal to dou v by dou y. The options here are v. We have to find the correct v which satisfies the given analytic function f of z. We are given u. U is equal to xy. So, dou u by dou x is y. We have to find dou v by dou y from the options. Which option will give dou v by dou y as y, which is the required answer. Check. X plus y the whole square is derivative with respect to y is 2 into x plus y by 2, which is now equal to y. Next one is x square minus y square by 2. That is differentiating with respect to y. Minus 2y by 2, which is equal to minus y. It is also not the answer. Next one is 2y by 2 is equal to y. So this is the answer. It satisfies the Cauchy Riemann equation. Dou u by dou x is equal to dou v by dou y. Next one also does not suit the requirement. So this is the correct answer. Next question. This is the next question. The complex conjugate of the function u is equal to 3x square minus 3y square. U is equal to 3x square minus 3y square. What we have to do is we have to find dou u by dou x, which is equal to 3 to the 6x. And our requirement is it should satisfy the Cauchy Riemann equation. Dou v by dou y. We have to find the complex conjugate of the function u, that is v. We can find which v satisfies this equation as the required answer. So from this we are taking the derivative with respect to y. This is equal to 3 to the 6y, which is not the required answer. This is equal to minus 6. This is 6, and this one is differentiating with respect to y, 6x. So this is the correct answer, which is the complex conjugate of u. V is given by 6xy plus k. Hope you are all clear with these portions. We will see more about these complex functions in the next video. If you have any doubts, please comment below. I will be clearing your doubts. Thank you.